Okay, so we're starting our afternoon session with Predrag Tanović, and he's going to talk about colored orders with equivalence relations.
First of all, I would like to thank the organizers. It's always a pleasure being in Wrocław all around for another theories.
Microphone, please.
Oh, microphone, yeah, microphone. Microphone? Works. Okay, so this title is a bit wrong, I kind of. Anyway, so I won't write it on the blackboard. But what is correct that this is a joint work with.
Could you write big letters?
Oh, sure, yeah. Large enough?
I'll wait to see this from the back.
Joint with Slavko, who's present here, Marconia, and there is another my student of mine, Dan, who is not present. So I'll present what we were doing in the past few years. Okay. So the topic is, oh, actually, this is not the topic. What's the topic here? So it is an old paper by Rubin. (1974), which is called Theories of Linear Order. Okay. So maybe the proper title of my talk would be something like this: on Rubin's theories of linear order. So something very old. What was the topic of Rubin's paper? Well, I will state the theorem, results, theorems. Okay. So suppose that this complete theory, complete and always in next hour countable, theory of colored order. Yes. Then first result of Rubin says that I of t aleph naught, which means the number of non-isomorphic countable models of t, is either 1, 3, 4 up to aleph naught, excluding aleph naught, or continue. Okay? And the other result there was the same, but now assuming that we have added only finitely many colors to the ordering relations, it says that the number is 1 or continuum. Okay? Either it is our zero categorical or has continuum many countable models.
What is the second one? What is the second one?
Well, I said what I didn't write. If the language is finite.
Ah.
So when we add only finite and many colors, we cannot have 3, 4, 5, 6, 7, etc. Okay. So, well, actually this is a very deep result for 1974. Why? Well, it's not easy to count countable models of theory, assuming that the theory has, say, aleph 0 countable models. It's not easy. Somehow one has to explain them in terms of certain invariants. Okay? So Rubin did it in 1974 for colored linear orders. Well, Baldwin and Latham did it for uncountable categorical theories just by specifying the dimension of the pre-geometry involved in any strong linear set up to that. Okay, well, these invariants are, for omega stable theories, they are much more complicated.
Is it true that the moment you name one non-principal type, it blows up? The next step, it has continued many types?
No, I didn't say, not type model. What?
Yeah, but you can prove it by counting types. So you add a name for one.
No, you have to worry about how do you put compose Aleph zero categorical theories, Aleph zero categorical models which are not isomorphic. So there is something fishy about this, and I won't spend too much time on this. So, okay, so in order to do this, Rubin had to understand definable sets in any colored order, up to some extent, but he gave no explicit description of definable sets.
In fact, you know, I think this was his master's thesis. It was his master's thesis, not even his PhD thesis. I think.
This is 50 pages long,
Yeah,
paper published.
It's amazing.
I don't know where, Transactions AMS. So they publish master's thesis.
Master's thesis.
Okay, so master students, you are encouraged. Yes, okay. Okay, so no explicit description of definable sets, although I say he had to deal deeply with the definable sets in colored linear orders. Okay? Okay. Who gave some explicit definition of definable sets? Actually, of two types was Poizat in his book. There is a small proposition where he describes two types. He has, say, A less than P, then type of A, B is described by type of A, type of B, and then by unions of all, well, I will write. So, by all possibles one types of chains between A and B. So all possible one types of chains between A and B. Okay. I mean,
You mean like sequences of types?
yes.
Okay.
But what is the context? What are the assumptions?
Any colored order.
Okay.
Okay, colored order is CO.
By order you mean partial order or linear order?
Linear order with unary predicates. So this is not so easy to visualize description. Okay. Oh, there is one really good. It is due to Pierre Simon on DP minimal ordered sets paper some, I don't know, 7 years ago or so. There is a little proposition giving description of definable sets in linear orders. And what is it? Now take any linear order, add all unary predicates. I mean, okay, imagine that we have some linearly ordered structure. Now extract all definable unary predicates and extract all monotone binary relations. Okay? All. Then this structure has quantifier elimination. Okay? So any linearly ordered structures, take whatever it has and just take unary predicates out of it, all of them, and all monotone relations. What is a monotone relation? Monotone relation on a linear order A is something, this is x and this is y, then it is something like this. Okay? Meaning that formal definition, I mean, these fibers are decreasing, non-increasing. Okay? These fibers, when you move there. But formal definition, it is a binary relation such that x prime smaller than x and x in relation with y and y smaller than y prime implies x prime is in relation with y prime. This says if you go left and up, you remain in the relation. Okay? It's some, I don't know, cells.
But for the quantifier elimination, you assume decommunality. The structure is decommunal or not?
No.
Oh.
No, the proof is you just push the quantifier through. So, I mean, syntax. No decommunality. Okay, so this is a very nice description. Okay, so now I can say what will I talk about. Okay. First thing I will I will give a bit more clear description, at least to me. This is clear enough, but it can be more specific a little bit. Especially this can be clarified. I mean, this can be given, be clarified even with Simons, not a problem. But, so, these two things, and finally, then something else that I won't say now, and after that I will try to count countable models not of colored orders, but of quasi-weakly or minimal theories. Doesn't matter what they are right now, but they include colored orders. That follows from Simon's result. Okay. So, the description. First, in order to also motivate that thing that I didn't mention what it is. Okay, now, why colored orders? Why not just orders, pure linear orders? That was a long time ago, noticed in the 60s when model theory of linear orders began. just notice that there are some pure orders. How to call them? Pure orders. The class of all of them is somehow equally complicated than the class of colored orders. They're not more, in general, all of them, not more complicated than this. Why? For example, any colored order with finitely many colors is a homomorphic image of a pure order. So, why is it a homomorphic image? Homomorphic in the sense of algebra, if we don't take a binary relation, but we take infimum as an operation, minimum of two elements, then in the algebraic set there is a homomorphism. If we have any linear order, say M, with some predicate P, then we blow it up. We blow every point up. Those points which are in P, we say replaced by a, I don't know, 1 point, then we put integers, and then one more point. And for points which are not in P, we be more generous, then put 2 points, then integers, and then 2 or 3 or whatever. Okay. And now we get this pure ordering, and there is a definable equivalence relation whose classes are precisely these ovals. Okay. Okay. So there is an equivalence relation which is convex. So convex equivalence relation on a linear order, by that I mean convex classes. Okay. And now quotienting the convex equivalence relation is a homomorphism of a linear order. And in fact, one can see that here, all the structure here comes from this homomorphism. There is nothing else. We can recover P. We have this, and that's it. Okay. So I guess something like this was observation made in 60s, 50s, or maybe, I don't know, which made people study colored orders, not just orders. Okay. And now, 40 years after, I would like to make another trivial observation. What do we call it? Colored orders. No, this isn't that. Colored orders with convex equivalence. So essentially, when we do that and we replace this, I mean, all these monotone relations. Sorry, any convex equivalence can be obtained from a monotone relation. But in general, monotone relations cannot be obtained from equivalences. There can be a proper translation. So okay. So there is theorem 1. Which says the same thing in any. No, I will write it as it is here. So we have any linearly ordered structure, and then we extract all the unary predicates and all the convex equivalence relations, and we have to add something like the successor function, which cannot be definable through convex equivalences. And the successor is, for each convex equivalence, we have successor relation Sj, so that two elements are related if they're x and y, if the y class is an immediate successor of the x class. So that cannot be eliminated, and this thing has quantifier elimination. Okay.
Okay, what is the structure consist of? Tell me what the structure.
What is it? So, I mean,
what do you mean all, when you say all?
so imagine that we have any linearly ordered structure, and we name all unary predicates definable.
So all, you mean all definable, you add predicates, add
All zero
Definable.
definable,
all zero, you add predicates for.
yes,
Okay.
all zero definable
Yes.
equivalence relations,
Okay.
and this is okay. Okay. Okay, so now there is a bit better here description of definable sets. So now in any definable set in colored ordering, say, is a boolean combination.
Could you write a little bit bigger, maybe?
Oh yeah, sure.
Well, this is okay, but you continue with bigger.
It's okay too, Krzysztof, you are in the second row.
You can just read it, you can just read this.
Any definable set in CO, boolean monoxide, is a boolean combination of
But now big.
zero definable unary, then classes of convex equivalences,
Zero,
I mean-
zero definable.
zero definable convex equivalences, and intervals.
Like in a CO or in a COCE?
It is the same.
Ah,
Definable.
So in any linearly ordered structure, whatever you have, I mean, there is something very trivial coming just from the order, unary predicates and convex equivalences, which,
okay.
I mean,
What you mean definable subset of collection of elements.
yes, of course. Classes of... So somehow, I mean, if we take, say, I don't know, omega squared, you have this function, the next limit point, okay, the successor limit point. Why do you have it? So you have a convex equivalence, extracting this thing which is discretely ordered. Okay? And then it comes as a minimal point in the next class. Okay. Okay, so this is one thing. Okay, what would be now the description of two types? Description of two types would be as follows. it will follow where? Okay, so two types. If you take 2 points A and B, first of all, if they do not have the same interval type, I mean, okay, that they are weakly orthogonal and there is nothing to describe. Okay. And just imagine for a moment, so the only interesting situation is when A is a realization of P, say, of one type, over the empty set, say, and the locuses of P and Q somehow are twisted. Okay? This is defined by interval types in Rubin, but that doesn't matter. Okay? So they are not weakly orthogonal. How do we describe all the possibilities? So here on this interval type, I mean on the convex, or in other words, the convex closures of P and Q are the same thing. It is a convex subset, so we have some convex equivalences, they are definable, and there is a linear order on them. Okay, so a proper convex non-trivial equivalence is definable here. And what happens with them is that this capital I is naturally ordered. Namely that if you take two distinct relations, then, sorry, is it ordered naturally? No. Yes, or not. Partially, but I mean, essentially it's linear. I mean, if we pass through subset. No, it is linear, come on, it's trivial. There is a linear order, so if I is distinct than J, then every on the locus are all the same type, but doesn't matter. Then each class, say I class is either split by EJ into infinitely many classes, and then monstrum many, or the other way around. In that sense, we have a linear order here. So what are the possibilities for type of A over B? So there is some maximal I. Maybe it's not, there isn't that maximum, but doesn't matter. Or sorry, there is a minimal I. No, okay, so we have just to specify classes. So we have to specify I's such that the EI class of A does not contain B. Okay? And else, if it happens that for some I, B turns out to get into the third class, then we have to worry about it. So the whole information is, so indices I for which A is in EI class and B is not, and then I and I mean the successor, the length of the successor function length, in which we can reach the B by this E class. This is so this is something like we have only successor function, and we have a linear order which measures sizes of these classes. So I guess this is much more clear visually than this one. Okay. Okay, so that's what I promised. That was the first thing that I promised. And now, about that thing that I have not formulated yet, let me say something. No, maybe.
So, so do you mean that like the type then only depends on like how many classes you have in between, like how many given by the equivalence relation EI?
I think so.
Yeah, it can happen. I mean, have in mind omega, and take 1 and 3. Here the equivalence is trivial, and you have to say, okay, I need 2 steps to reach B. Good. It can happen that it's not points, but successive classes. And then you have to worry about that. If that happens at all. I mean, otherwise, it can be just specifying the classes which contain A but not B. All of them. That's some initial part of this linear order. And that describes the type.
And this follows from the previous theorem?
Yes. 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 Okay. No, I don't want to erase this. I will erase this again. Okay. So. Okay, the next task was to somehow to describe some via automorphism property of structures like this, or just of pure linear orders, certain property. And that was not our intention, but it came out of studying Rubin's arguments. I mean, they were made in 1974, they're very neat, etc. But from the very beginning, when we started from here, I knew that there is some other presentation of these results due to asymmetric regular types, global, discovered by Anand and myself some years ago. So that was the original motivation. Okay, so what Rubin was using to prove this, he used syntactic methods. And there is something there which is called testing formula. It's not important essentially what it is, but but this is some strong form of stable embeddedness of convex sets, expressed in a 6-line long definition with something, so it is not important. No syntax is needed. Okay. And there was one semantical condition which I will label now. I will call it linear binarity. What is it? So, he proved that any color order has the following property, that whenever we have a finite increasing chain, then the types of consecutive pairs determine the type of the whole tuple. He called it binarity, but nowadays we By a binary theory, we mean theory where, well, one way to describe for any tuple, the pairs of, the types of all pairs determine the type of the tuple. Equivalently, any formula is equivalent to a Boolean combination of formulas with at most 2 free variables. So, actually it was not he said that it was Fred Galvin who, before him, noticed this property of colored orders. So this is a very nice property. I mean, so it became quite natural to see, okay, does this characterize linear orders, or there is something else, something complicated that can satisfy this linear binarity. I think I would call it LB. No, not to be okay. So there is something very stupid which satisfies linear binarity and which is kind of not precisely like a colored order. So we take rationals and just add the equivalence relation with 2 dense classes. This is not the homomorphic, full homomorphic image of any pure linear order. I can bet on it. So, I mean, yeah. Okay. So, it satisfies this linear binarity, but kind of, let's say it is a bit more complex. It is interpretable in a pure linear order, but it's not a homomorphic image. Okay, so this has LB, but if we have the same thing with 3 classes, it does not. Okay. So, I mean, even this distinction says that this is not probably the best condition. Okay, so what is the condition that characterizes? No theorem. I will write now the full theorem. Suppose we have a saturated linearly ordered structures satisfying the SLB condition. What is SLB? It says the following, for any convex C subset of U and any F automorphism of U of this structure such that fixing C setwise, comma, the following now, if we define G by F in C and identity outside C is an automorphism. Okay. Any convex set, any automorphism fixing it setwise, if we extend by identity outside, then we again get an isomorphism. Automorphism. It is. Okay, maybe you don't see why is this S of that. S means strong, it's not W. So this is something, let's call it strong linear binarity. Oh yes, I haven't completed the statement of the theorem. Oh, it's very bad now. Okay, I can go upstairs. No, no, I won't. Oh, I will use this. Then if you take now these all definable unary predicates, all definable convex equivalences, and add this, well, actually we don't need this. Then this structure with all named definable unary predicates and convex equivalences is definitionally equivalent to the original structure.
What was the original language?
Any
Any.
countable thing. It doesn't matter. Okay. So whenever saturated structure has this property of automorphisms, then it essentially is just derived from a pure linear order. Okay. Okay. So that's theorem 2. Okay. Oh, I see. Okay, so then, okay, now the question is, so as strong linear binarity characterizes this simplest linearly ordered structures, the question may be asked, what about linear binarity? Which structures satisfy that? And actually, what turned out is that that definition of linear binarity is not so useful as it is nice at first glance. So you can characterize that in terms of something more complicated, but there is another thing which is also nice, but also has some strange characterization, which has the following. Now we have any linearly ordered structure. Now consider condition F, saying that for any formula phi with and any separation of its variables and any little a from du. So I'm assuming that we are in the monster. See? There are only finitely many phi types over with parameters from everything smaller than a, any or including a parameters there that are realized after a, in a plus infinity.
Do you mean that every tuple comes from every?
Yes, yes. Every tuple comes from here, and every tuple comes from here. Okay. This is a kind of associated with something that Rubin used in his proof. One of the syntactical things. It looks strange, but also it seems to be satisfied only in some trivial structures. It is like that, but unfortunately it does not imply binarity of theory, even in the other zero categorical case. Okay. So somehow this one is weaker than these two, and the actual strength is that F implies LB. No, of course not. So the other way. SLB implies LB implies F. Okay. I think that I'm not going to explain much of this. Okay, for this, just look at this as if we have bipartite graph. Vertices greater than A, one sort, the other smaller than A. So there are finitely many phi types, and then it will become a bit more clearly. Okay, so strength is like this. Unfortunately, I'm not going to state characterizations of these things because I don't have time, and they are not so interesting. One has to add not convex equivalences, but something which is called almost convex, which means that equivalence relation which has finite index in its convexization. There is the smallest, for any equivalence relation, there is the smallest one with convex classes containing this one, and now the old one has, in each class has finite index. And then one has to also to fiddle on the, to worry about the algebraic, about some finite structures there, and it's not so interesting for me. And it's ugly, so I will stop now speaking about this topic, and I will switch to Watt's conjecture.
What is the point of talking about this condition F? Why did you mention condition F?
Yes, because I wanted to stay also some theorem about it. There is something like this about it. But you have to add here not convex, but almost convex equivalence relations. And maybe, maybe something more.
These i's are not just convex, but something else?
No, in another version.
Oh, in another version.
In another
Under
version.
F,
If we assume F, then we have to add that plus some some finite structures. Anyway, I mean, okay. So one would expect that this linear binary, that it has a nice description, but it does not. It is not as nice as this one. Okay. Now I will switch to Watt's conjecture for quasi-weakly or minimal, or weakly or minimal, doesn't matter. So, number of countable models of weakly or minimal theory. Okay. What we did on this topic, there were two things. First thing, we merely reduced to the binary case and the second thing, we proved the binary case. about the proof of the binary case, Slavko was speaking in Wrocław. So I will say only a few words about this reduction, which is in my, but I don't have time to prove anything. So nearly, so what does this mean? What do I mean by nearly? I will try to explain. Okay, so there was an attempt to classify weakly all minimal Aleph zero categorical theories by Berkhard, Herbert, Dugald, and others. So they classified the binary case. Classification is possible. And then they found a non-binary example by adding some C relation. Then they noticed that four relations can be probably added and whatever, and they gave up. Okay? So they nearly reduced the classification of Aleph zero categorical weakly or minimal structures to the binary case. In that sense, we did it as well. So what is the technical result here? Technical result which explains this near reduction is the following. So assume that we are weakly or minimal with few countable models. Then, and consider set definable by a single parameter A, which realizes P, and this set is, now this is a locus of P. Now this A is here, and phi of the A of U is like this. So it is convex, starts at A, and has an upper bound in P. Okay? The near reduction says that all these things call this set D are of the form A plus infinity intersected with E of A U. So there is a convex equivalence relation E. So that this phi is precisely the phi of A U is the part of E on the right side of A. This means, I mean, if we are all minimal, then this means that there is no translation in that all minimal structure. By translation, I mean unary function from the locus of the type into itself.
So you're assuming here a few models, you didn't say?
Oh yes. This is important. Okay. Okay. So it does not have to. It can have weakly or minimal can have this property and still not being binary.
Wait, but D is a subset of the locus, or?
The D is equal to this thing. I mean,
Okay, sorry. Okay.
this thing.
Yeah, I'm asking if D is a subset of locus of P.
Yes.
Okay.
Okay. Maybe the proof of this is, I mean, there is a nice trick in there. So maybe, I don't know, maybe not. Okay. Okay, I will try in the next 2 minutes. Okay. So suppose this is not the case, then if we look this phi as a binary relation, then we can conclude that if we make powers of phi, then we have to grow up. Okay? So we get some sets whose supremes are growing up. Okay, take a limit here. Absorb this into the language. And takes the closest
What do you mean about power?
composition of binary relations. It grows. Because it's on locus of the same type. Okay? Grows. Now somehow take limit here. I mean take complete type which is finitely array which is finitely satisfiable in here. And now consider only things on the left of A and say not far from here. Any set definable, literally any set, intersecting the union of this phi to the n's has a phi minimal element. What do I mean by a phi minimal element? It is element in that set such that if we go by phi inverse, then we get a lower bound for that definable set. Okay.
Could you repeat, please?
Okay. On this picture, this guy is phi minimum. If we go by phi inverse, then we get something which is smaller than our definable set. So somehow this is phi minimal. It's like, I mean, we don't have minimal elements with respect to this order, but if we incorporate this phi as a translation, then we can have it. Okay? And since this is finitely satisfiable, the same thing comes here. Also, any definable set intersecting the locus of this type has a phi minimal element. And now we have some global invariant type extension of this, actually left extension, that is finitely satisfiable in here. Then we prove that it is trivial by, I mean, just contradicting smallness. And then having the trivial global type which we consider non-forking there, and then it is not simple in the sense that Slavko was speaking in Wrocław and I don't have more type, it's not simple. Anyway, so what was nice here, so this is this phi minimal. So it's like in omega, when you take any subset, you have the minimal element, so when you pass to elementary extensions, any definable subset of the universe has minimal extension or value, so yeah, thank you very much.